2, 1. Alright, here we go. The first pre-recorded lecture of Math 317, Fall 2022. Alright, hopefully the only one. We'll see. We all got some sort of wonderful stomach bug. So, if I'm a little low energy, that's because I haven't really eaten anything in a while. So, anyway, alright, let's get into it. Alright, so what are we doing? Alright, the goal for today, so we kind of left off with a cliffhanger on Friday, talking about Gram and Schmidt and the process associated with these two. Alright, let's remind ourselves of where we're at, what we're doing. Okay. So we're hanging out in inner product spaces, and at this point, hopefully we're all on board with what that is: a vector space equipped with a function that spits out real numbers given two inputs from the vector space that satisfies a particular list of things. And again, the goal of an inner product space is to basically have access to geometric ideas in our vector space. So, as we've already seen, the inner product can be used to give us length by looking at the norm. And now we're after how do we get angles. In particular, we're after pi over 2, so specifically when things are perpendicular, also known as orthogonal. Alright, so a list of elements in an inner product space is said to be orthogonal if the inner product is equal to 0 for two elements with different indices. And we gotta stress this part here, right? And we need to stress this part here because if I didn't include this, if I just said you're orthogonal if the inner products are all equal to 0, well, that would mean that VK inner product with itself is equal to 0, and as we already discussed, with an inner product, that means that the element must be the identity. So then, if we did not include this indices are distinct requirement, then our list would just be all identity elements, and that's not a good definition. Alright. Okay, and something else to note, right, so this is true for a list. So you're orthogonal if given a list, the inner product of any distinct pairs is equal to 0. So because of that, worth stressing that a single element list is automatically orthogonal, right? Because I can't choose two separate indices, so right, the definition is just automatically satisfied. Okay, and if I have a pair, then I just need to check, yeah, the inner product is equal to 0. And if I have 3, well, then I've got 3 things I need to go through. If I've got 4, well, there's more than 4 that you gotta work for. But yeah, so, right, when we say list is orthogonal, what we're really meaning is we're just getting at all of the pairs that you've got. So you look at all your pairs, and if all of the pairs, now, again, distinct pairs, I don't care about V1 inner product with V1, I don't care about V2 inner product with V2, right? I care when the indices are different. And as long as all of those are equal to 0, I'm happy. That means I'm orthogonal. Cool. Alright. Now, alright. So this is our notion of geometry in inner product spaces, right? This is our notion of angle that we're going after. Okay, so why should we care about this? Well, last time we proved a very cool fact. If I have a orthogonal list and everything on my list is non-zero. Now, note the definition allows 0 to show up in the list. And in fact, if you have an orthogonal list, then you can add as many zeros as you want and it will still remain orthogonal. But if we have a list of orthogonal things, none of them 0, then we are in fact linearly independent. And in fact, we got this using the Pythagorean theorem. Cool. Alright, so that means if we have an orthogonal list, we've got a linearly independent set. So if we were in a, n-dimensional vector space, then having a list of n orthogonal things, all of them non-zero, would then give me a basis. Nice. Okay. So that's going to be our goal for class on Tuesday, actually, is to attach orthogonality to bases, and we're going to prove a really cool theorem called the approximation theorem. But before we get there, let's get to the star of the show. So, note, orthogonal and non-zero gives me linearly independent, but as we discussed in class, linear independent does not mean orthogonal, right? It's pretty easy to cook up elements in R2 that are linearly independent, but the angle between them is not pi over 2. So, you can't just say any linearly independent set is orthogonal. However, every linearly independent set gives rise to an orthogonal list that has the same span. And this is the Gram-Schmidt process. Alright, cool. Alright, so for any inner product space, if you have a list of linearly independent things, basically you can go ahead and replace them with a list of orthogonal things. Note that the spans will be the same. Right. So in other words, if I do have a basis of n elements, so if I have an n-dimensional vector space with a list of n elements as a basis, I can actually turn it into an orthogonal basis. And again, the power of an orthogonal basis is going to become much more apparent when we get to the approximation theorem. So for now, just trust me, bro, we totally want this. And especially during the proof of this, when you see what you got to do, trust me, bro, this is going to be the shit. Alright, so let's go ahead and prove this. So, like I said, the proof of this is not going to be, awful, or as I've been hinting, it's not going to be, terrible. What you're about to see, though, is going to be like, oh, great. So, let's just jump right in. Alright, so we're going to proceed inductively, right? So, note that, for the base case, as we already noted, a single element is orthogonal, and V1 is linearly and the x's are linearly independent, so that means they're all non-zero. So, yeah, if I only had one thing, I can easily turn it into an orthogonal list. Alright, so we did the base case. Now the induction hypothesis. Suppose that we've constructed m orthogonal things, all of them non-zero, and the span of all of them coincides with the span of the original list of linearly independent things x1 to xm. So the only thing I need to do is tell you, how do I make Vm? So what do I need to do? I need to construct a Vm that is non-zero, orthogonal to V1 to Vm, and the span of V1 to Vm plus 1 is the same as the span of x1 to xm. Okay, so how do we make it? Well, that's how you make it. Oh, and I wanted to pause there. Boo. Alright, well, too late. Deal. Alright. So, okay, here is how you actually create the Vm plus 1. You take xm plus 1, and then you subtract this off. Now, why do I subtract this off? Well, it works. That might be a very unsatisfying answer. But there is reason to subtract this specific thing. So, like I said, in a moment you're going to see this is exactly the right thing. But if you want some intuition of where this comes from, as I hinted when you took Calc 3, you talked about projecting vectors onto another one. This is like, oh, I don't know, projecting a vector onto, like, a span or something. Ooh. We're going to get into that in a lot more detail on Tuesday. If you want a little bit more geometric intuition, your book draws a nice little picture of it. I'm going to save it for class on Tuesday. But, yeah, for now, just kind of accept this is the right thing. This just ends up working, and we're going to dig through it. Yeah. Alright. So, first things first, I claim this is what works, and as I already revealed, I got three things I gotta do. I gotta show Vm plus 1 is non-zero, it's orthogonal to the other elements, and the span of V1 to Vm plus 1 is the same as the span of x1m xm plus 1. Alright, so first thing first, let's say this was equal to 0. Well, that means xm plus 1 is this linear combo, and that lives in the span from V1 to Vm, but by hypothesis, that's the same thing as the span of x1 to xm, which would mean that xm plus 1 is a linear combo of x1 to xm, and that's going to contradict that what I've got is a, and that should be an n, actually. Let me fix that. And that contradicts that the original list is linearly independent, because we have an element is a linear combo of the others. So, and as we proved, that would mean that you are dependent if one element can be written as a linear combo of the others. Alright. Alright, so it's got to be that Vm plus 1 is in fact non-zero. Cool. So, excuse me. Point 1 accomplished. Point 2, let's show that the list is orthogonal. Okay. So first things first, we know that V1 to Vm is orthogonal, which means that the inner product of Vj and Vk for any j running from j and k running between 1 and m, where they're different, that's always equal to 0. So the only thing I need to verify, because inner products again are symmetric, I just need to verify that Vj inner product with Vm plus 1 is equal to 0. That's good for every j less than m. Because obviously, again, we need the indices to be different, right? And we already know that every other possible combo zeroes out. So I just need to see how m plus 1 is going to interact when we add it to the list. All right, so we're going to look at the inner product of Vj and Vm plus 1. Remember what Vm plus 1 is equal to. It's equal to this. And now, why this is the way it is becomes apparent. Okay, so again, let's break it down a little bit here before we get into it. So we're taking the VKs and we're scaling them all by a very particular thing. So first of all, note here, this is the norm squared of VK. All right. Seems like maybe a reasonable thing to scale. But here you've got kind of an interesting thing. You've got the inner product of VK with xm plus 1. All right, well, remember inner products break up over summations. We could pull scalars out, so that happens. And let's do it again. And now, after we've kind of pulled it apart, now you sort of see the genius of it. Hey, these are going to zero out for every k that's not equal to j. So what do we pick up? Oh, hey, Vj xm plus 1, Vj xm plus 1. Those would cancel out if I didn't have the Vj Vj. Now remember, for an orthogonal set, right, we don't know anything about the inner product of the element with itself. We know that our elements, by hypothesis, are non-zero, so the inner product of them with itself is not equal to 0. But we don't know what this is equal to. But good thing we divided them out to ensure that, hey, they cancel and we get 0. So here we see that this sort of concoction immediately gets us that the VM that I made here has to be orthogonal. Like, by its construction, the orthogonality happens. So we can kind of see some justification for why this ends up being kind of the right thing. And again, your book has some geometric drawings if you're so interested in that. We're going to, like I said, dig in a lot deeper into what this expression is and why you would even think to work with this thing in a little bit. You kind of need the we're kind of doing it backwards. You kind of need Gram-Schmidt in hand to sort of justify why you would care about this. And then we're talking about why you care about it. All right, but here we see that this exact expression is what we needed. So we've got the Vm plus 1 is non-zero. We've got the inner products are equal to 0. So now we just got to verify the spans line up. Okay. So note that xm plus 1 is Vm plus 1 plus all this junk. So, hey, note that would live in the span from V1 to Vm plus 1, because it's a linear combo of the elements from V1 to Vm plus 1. Now, by, it should be an M. Man, doing great with the M's and the N's today. All right, the span of x1 to xm, by hypothesis, is the span of V1 to Vm. Note this is contained in the span of V1 to Vm plus 1, because it just added one more element, so the span got bigger. Alright, but where does xm plus 1 live? It lives in the span from v1 to vm plus 1. The span of x1 to xm lives in that same span, so the span of x1 all the way up to xm must also live in that span. Right, if we throw this element in, well, it already lives in this set, so it's got to remain in the span. Again, span being the smallest subspace containing these things. Alright, and now we get equality, and we're done. Proof's over, right? And why does that happen? Well, by hypothesis, we know that this is a linearly independent list. And since these are orthogonal and non-zero, we also know these are linearly independent. So here we have a span of m plus 1 linearly independent things containing the span of a list of m plus 1 linearly independent things. These spans must be equal to each other. Right? Because this right here would be an m plus 1 dimensional vector space. And this tier 2 would also be a m plus 1 dimensional vector space, so we have to have equality. If we do not have equality, then I can find something in here that I can add to this list that would make it linearly independent, but that would mean I'd have more linearly independent things than I use to span, which can't happen. Beautiful. And there we go, the Gram-Schmidt process taken care of. Given any list of linearly independent things, we can just replace them with orthogonal ones and get the same span. Alright, now the nice thing about this proof, right, let's go back to the statement. The statement is, there exist things that do stuff. And this is a great example of a constructive proof, because I actually told you how to make them. Right, so in math, whenever we have a there exists, one of two things goes down in a there exists proof. There is either a constructive proof like this, where I give you like an algorithm. I give you like just straight up, here's what you do to get the things that I claim exist. There are other there exist proofs where you're not so lucky, where you just sort of logic the existence and you don't tell people how to get it. And that was a point of contention for a long time in math, of kind of like, if you claim something exists, you gotta show me how to make it. But that kind of got in the way of good mathematics, so it kind of went to the wayside. But there are people that are really focused these days on the constructive side, like what math can really be actually made in sort of this sense. Good stuff. Alright. So because the proof is constructive, I can actually show you how to do the Gram-Schmidt process. If I give you a list of linearly independent things, here's 3 linearly independent things in R3, you can verify these are linearly independent. So again, note, Gram-Schmidt can only be applied to a linearly independent set. Note that we use the linear independence in the proof. So you cannot apply Gram-Schmidt to linearly dependent things. I mean, you could, but stuff probably goes haywire. So for example, probably what would happen is one of the elements along the way is going to equal 0. So, right? Because remember, in the proof, we use the linear independence to verify that the added element is non-zero. We also use it to show the spans line up. So, anyway, all right. So, all right. Let's. Hey, look at that 7 pause. That's, oh my god, high quality. This is your tuition dollars right there. Alright, so, alright. Now, I'm going to label this one X1, this one X2, and this one X3. It actually does not matter the order in which you label them. The process will work all the same, but I have first, second, third. Why would I choose another way of doing it? Alright, so first things first, the easiest step in the Gram-Schmidt process, V1 is X1, right? We saw that in the proof. That's the base case. They just pick it to be V1. That's it. Alright, so now how do you create V2? Well, V2 is created by taking X2 and subtracting off the expression from the proof. Specifically, V1 scaled by this. And now, like I said, if you've taken Calc 3 before, this is uncomfortably familiar to you. Right, this is right, taking an element and projecting it onto another one. And again, we're going to get into that in a little more detail in class on Tuesday. Right. And again, your book's got some solid pictures of this, so check that out. Alright, so, right, you just go for the computation, and you pick up this element, and then we make V3 by, again, just going to how the proof said what to do, and just compute the elements, and some arithmetic happens, and bam, here you go. There we go. Gram-Schmidt process performed. Right, and my promise to you is that I'm only ever going to make you do it by hand for 3 elements. I will not subject you to 4, because oh my god. I could do 3 elements in R4. That'd be awful. No, 3 elements in like R7. That'd be oof. Yeah, but so as you can imagine, right, if you've got a, let's say, 20 element list, you got to do this 20 times, and oh boy. Oh boy, right? Oh boy, Alberto with that one, yeah. Okay, so, yeah, that being said, we still got a little bit more slides to go through here. So, for those of you keeping score at home, you may have noticed that my version of Gram-Schmidt is a little bit different than how the book does it. Because the book presents Gram-Schmidt without having to deal with this expression in the bottom. Right, so if you look at the book's version of Gram-Schmidt, these things in the denominator don't show up. What's that about? Alright, so a list, and these live in V. I mean, obviously they live in V, but for preciseness, let's keep it in there. Olive, my cat showed up, so you can't see her, but I have a cat sitting on my lap right now. Alright. So, a list of elements, U1 to UN, in an inner product space are called orthonormal if their inner products behave as follows. So, for the indices being different, they're equal to 0. So note every orthonormal set is orthogonal. But now I'm going to throw in a requirement about what happens when the indices are equal. The inner product is equal to 1. So in other words, the norm of every element is equal to 1. And those are called unit vectors. Okay, cool. All right, so before we continue, I want to complain about this name here. So it's called orthonormal, right? Because how else would you pronounce this? Well, orthonormal ruined me because after I learned the word orthonormal, I started calling this orthogonal instead of orthogonal. Right, we got orthonormal, so, right, for consistency, this needs to be orthogonal. Come on now. So I got into the habit of calling this orthogonal for the longest time, until, so as I've mentioned him, the professor I took this class with way back in the day was a guy named Professor Fulton, and I was sitting in office hours once, and I said orthogonal in front of him. He put his arm on me, looked me dead in the eye, and said, "Chris, never say that again. It's orthogonal." I was like, okay. But anyway, right, so orthonormal, bleh. So we got this. Okay. Now, as we're going to see, orthonormal is in fact better than orthogonal. Orthonormal is actually going to make our lives a lot easier, and in fact, kind of makes the Gram-Schmidt process a lot easier, too. Alright, because here's what happens. If I have a orthogonal list that are all equal to non-zero, I can actually turn that into an orthonormal list by just dividing out by the norms. Because again, this requirement here that the inner product of the element with itself is 1 is just requiring length is equal to 1. So if we have an orthogonal list, I can make it orthonormal by just dividing out by the norms. Good stuff. And the real power of orthonormal is right here, and that is that if you do have an orthonormal list, then note, any element that lives in the span must be a linear combination of the things. Now recall, by definition, span is just your linear combo, so there are scalars. An orthonormal list, there are very specific scalars. So not only do I know you're a linear combo, I can tell you precisely what your scalars are. And this is the first time we've seen something like this, where I belong to a span and I have an immediate way of communicating the scalars. That is very powerful. And, X inner product with UK, scaling that by UK. And if we go back to the proof here, like, oh, look, isn't that exactly what I did? Yeah. Oh, yeah, it's all coming together. Alright. So, alright, we're not going to prove that a orthogonal list here can be made orthonormal, and we'll justify why we would really ever care about orthonormal. And it turns out this particular expression, something similar, showed up in the proof of the Gram-Schmidt. So, in class on Tuesday, when we start talking projections, we're going to see this is the right thing. And we're gonna prove some shit with this. Alright, but before we get there, let's get used to orthonormal things. So first of all, let's prove that if I have an orthogonal list, I can make it orthonormal by dividing things out. So pick two indices. I have two cases to consider. Orthonormal requires that if they are equal, then I get 1. Alright, Well, if I look at the inner product of u and j, uk, uk, so remember how these are defined. This is just taking the vk's and dividing it by their lengths. I've got 1 over vk, 1 over length of vk, so I can pull it out. I can pull out 2 of them, so I got it squared. And oh, wouldn't you know it, the inner product is the length squared. So, ba-boom. That divides out and gives us 1. Beautiful. Almost as if it was intentional or something. Yeah. Alright. Now, if the indices are different, okay, well, then we pull a similar trick. We pull out the norms, but the list v1 to vn was orthogonal, so the dot products there are, the inner products there are 0, so there we go. My list u1 to un is orthonormal, because not only are the distinct indices inner product of 0, when I inner product an element with itself, it spits out 1. Cool. Alright. Now, for the real money result, a orthonormal list, the elements in the span, note, must be a linear combo, but I'm going to tell you exactly what those scalars need to be. Fix a j, and I'm going to m. It needs to be n. Oof. Where is it? There it is. Yeah. A little inconsistent with the m's and the n's today. Alright. Okay. Well, what do we know about my list? I know it's orthonormal, so uj inner product with uk is equal to 0 whenever k is not j, and uj inner product with itself is 1. So if I look at x inner product with uj, x is equal to this. Inner products, I know I can pull out summations and pull out scalars, and here these inner products here will zero out when k is not equal to j. And when k is j, the inner product is 1. So it just spits out alpha j, and there we go. So here we see the power of orthonormal sets. They allow us to explicitly tell you what elements live in your span. And like I said, that's going to be a very powerful tool when we start talking projections, which is what we're going to do on Tuesday. Alright, well, let's wrap things up by pointing out that point 1 of the previous proposition ensures that I actually have an orthonormal version of the Gram-Schmidt process, because I can start with a linearly independent list. Independent. That's some good, some copy pasta right there. Okay, let's fix that. I had it typed wrong earlier, and I copied and pasted it, and I fixed it, but I didn't fix it later. You know how it goes. Alright, so normal Gram-Schmidt is if I have a linearly independent list, I can create a orthogonal list of non-zero things with the same span. We just proved that if I have an orthogonal list of non-zero things, I can divide out by their lengths and I get an orthonormal thing, and dividing out by lengths is not going to mess up my span. Right, because I'm just scaling my individual elements. The span is just the linear combos. The scalars I'm using are non-zero, so they can be adjusted. Alright, and this is the version of the Gram-Schmidt that appears in your book. Your book does the orthonormal version. This will, and when we can line up the book's version of it with our version of it, and basically what you do is that you just normalize the vectors as you go along. So in other words, you take your elements, we perform our usual Gram-Schmidt, but we're going to divide out by the lengths at each step. Okay, so x1 is what v1 should be, but we then divide out by its length. That makes our u1. That gives me this. Our v2 then will be equal to this. Now note my u1 has been normalized, so u1 dotted with u1 is equal to 1, so I don't need to include it. Right, and that's kind of why the orthonormal version is a little bit stronger, because we get this element now. But kind of the drawback is that when you do divide out by lengths, you are invariably bringing square roots to the party. So if you don't like square roots, then yeah, maybe not gonna have a good time. But anyway, so that's how we get our u2. And then we create v3 by performing the usual Gram-Schmidt process with u1 and u2 in place of v1 and v2. Now note, u1 and u2 are, again, unit vectors. They have length 1, so I don't need to do any divisions. Alright, and, well, again, the problem is that square roots show up now. So the mathematics you gotta do, the algebra and arithmetic, a little more complicated, but not awful. But anyway, you pick up your V3, and then to finish things off, you divide out by its length, and then that's missing. Yeah, you know, 1 over a real number is equal to an element of R3. Hey, what's up? Told you I wasn't feeling good. Although I think it's in the type notes that I already posted, so you don't know that. Anyway, there you go. Beautiful. The Gram-Schmidt process now under our belt buckle. So we now know that if I have a linearly independent list, I can reject it and replace with an orthonormal list. And as we're about to see, having an orthonormal basis is a powerful thing. Turns out there's something really cool you can do with it. Something so amazing and so mind-blowing that you're going to have to just come to class on Tuesday to see it. Alright. See you then.